Hello and welcome everyone. This is the introduction to the course titled Optical Methods in Fluid and Solid Mechanics. I am Professor Alok Kumar. I am an associate professor here in the Department of Mechanical Engineering at the Indian Institute of Science. I will be taking the first part of this course. Now, as the name suggests, we will be primarily looking at use of optical methods for quantifying fluid flow. Now, in the recent years, optical techniques have come into vogue in experimental techniques, especially because their ability to provide full field measurements. If you are familiar with some of the older techniques, you might realize that some of the older techniques used to provide only point data or point measurements. So, as such, these full field measurement techniques have become extremely important. These full field techniques require a significant amount of experimental skills, but they also require a significant amount of theoretical understanding so that you can adequately post process the data. Often the post processing is in terms of image processing for us. Now, the data that you get, which is for example in the case of fluids, it just might be the full velocity field. These are useful in techniques such as particle image velocimetry. These techniques are nowadays very widely used in the industry, especially the aerospace industry, industries dealing with construction of ships, industries dealing with manufacturing of cars, and many others. In fact, these techniques that we are going to talk about, they are not that dependent on the size of the experimental setup, which means that some of these ideas that we are going to look into can be extended into the micro domain also. So, for example, fields like microfluidics, which utilize fluid flow at a very small scale, can also utilize some of the optical diagnostics that we are going to discuss in order to analyze data. So, the applications, as is suggested by this, the applications for some of these optical diagnostic techniques can range, especially in the case of fluid mechanical phenomena, they can range from all the way down to small microfluidic channels to large scale objects, for example aircrafts. We will also be doing lab visits because as I said, some of this much of this course will require data that is acquired in the labs. So, we will have a lab section where we will familiarize you with some of the nitty-gritties of acquiring data in the lab. The second part of this course is going to be taken by my colleague Professor Kaushik Vishwanathan, and I will request him now to speak on about his portion. Yeah, thank you.
Hello, my name is Kaushik Vishwanathan. I am also a faculty at the Indian Institute of Science in the Department of Mechanical Engineering. As my colleague Professor Alok Kumar mentioned, I will be teaching the second half of this course on optical methods in fluid and solid mechanics. My focus will mainly be on techniques that are applicable to solids, because that also constitutes some part of our group's research work. There will be three broad techniques that we will discuss. The first will continue from some of the PIV methods that Alok will discuss. It is a suite of techniques called digital image correlation or DIC. We will spend a little bit of time setting up DIC, formulating the problem, writing down some governing equations, seeing how we can recover fields and seeing how it is different from imaging fluids and from recovering velocity fields in fluids. The second part will take a slightly complementary approach. It is called the technique is called photoelasticity. It directly measures the stresses in materials that do show this phenomenon called birefringence. I will discuss that at length. We will explore some of the basic microscopic ideas underlying the phenomenon of birefringence, underlying what is called the stress optic law and things like that, and we will see how to interpret some of these images. And the third technique will be sort of larger than the other two, because it is a little bit more widespread and it finds wider applicability. It is called tomography, or we call it optical tomography, but the technique underlying this method is general to all sorts of applications, ranging from computer tomography that you would do in a CT scan, for instance. CT stands for computer tomography. So, it has applications in medical, in biomedical, in biological imaging, in addition to being applicable for evaluating internal structures in solids such as cracks, pores and things that you can't see on the surface. So it's a three-dimensional technique. It's a little bit of a deviation from the other two, but it will complete this suite of techniques that are usually applied for understanding deformation and structure in solids. Now solids themselves present very unique challenges compared to fluids. Most of you probably know from an early undergraduate course or from high school that fluids take a shape of a container and solids don't. So it's usually the type of kinematic variables that you have for a fluid flow are very different from the type of complexity that you will encounter when looking at solid deformation. So I'll start off by introducing some of these ideas in a more broader context, and then we'll delve into each of these techniques one by one and spend a little bit of time on each of them. We'll also round off our discussion in the lectures using some lab demos analogous to what Alok was referring to. We'll show you some examples of real life applications, some data sets that you can directly look at and see where some of these techniques find application, and also some segues like I mentioned into biology and biomedical instrumentation. So with that we'll round off the course, and I look forward to seeing you for the entire duration of the course. Thank you.